The Fast Lane. TLS 1.3 Session Resumption. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving into one of the most powerful performance features of TLS 1.3, which is session resumption. We have already learned that the standard TLS 1.3 handshake is fast, taking only one round trip. But what if we could make it even faster for returning visitors? This presentation will explore the mechanics of session resumption, the groundbreaking zero RTT feature it enables, and the critical security trade-offs that come with this incredible speed. The problem: the cost of a handshake. While the 1 RTT handshake of TLS 1.3 is a massive improvement, it is not free. Every new connection requires a series of cryptographic operations: 2 ephemeral key generations, 1 digital signature, 1 signature verification, and the Diffie-Hellman computation itself. On a high-latency mobile network, even one round trip can feel slow. For a busy server handling thousands of connections per second, this computational overhead can add up. The goal of session resumption is to create a secure shortcut that bypasses most of this work for clients that have connected recently. The goal: a VIP pass for returning visitors. The core idea behind session resumption is to give a returning client a special pass to get back into the secure session quickly. Instead of going through the full security check every single time, the client can present a VIP pass from a previous visit to get fast-tracked. This aims to reduce both latency, by minimizing round trips, and computational cost for both the client and the server, all while maintaining a very high level of security. The mechanism: PSK and the session ticket. TLS 1.3 unifies session resumption under a single mechanism called the pre-shared key, or PSK, exchange mode. Here's how it works. After a successful initial handshake, the server can send the client a session ticket. This ticket is an encrypted, self-contained blob of data that the server can decrypt, but the client cannot. Inside this ticket is a crucial piece of information: a pre-shared key. This PSK is a secret cryptographic key that can be used to bootstrap a future session, along with other data such as the chosen cipher suite and a ticket lifetime. Walkthrough Part 1. Establishing the ticket. Let's walk through the process. It all starts with a normal, full 1 RTT handshake. The client and server perform the ECDHE key exchange, verify certificates, and establish a secure session, just as we've discussed previously. The new part happens after the main handshake is complete. The server, knowing that the client supports session resumption, generates one or more session tickets. Each ticket contains a new PSK derived from the main session secret. The server encrypts these tickets with a key known only to itself and sends them to the client. The client stores these tickets, but it cannot read their contents. Walkthrough Part. The resumption handshake. Now, imagine the client reconnects a few minutes later. This time, in its very first client hello message, it includes the session ticket it previously received. It also includes a binder value, which is an HMAC that proves the client is the legitimate owner of the ticket. The server receives this, decrypts the ticket using its secret ticket key, and extracts the PSK if the ticket is valid. The server now shares a secret, the PSK, with the client. It can immediately send back its server hello and finished messages, deriving the new session keys from the PSK. The handshake is complete, and it was much faster and cheaper than the first one. The ultimate speed boost. Zero round trip, zero RTT. This PSK mechanism enables an even more powerful feature: zero round trip, or zero RTT. What if the client is so confident that the server will accept its ticket that it doesn't even wait for a reply? With zero RTT, the client sends its client hello with the session ticket, and immediately follows it with the first batch of application data, encrypted with a key derived from the PSK. This allows the server to process the request and potentially have a reply ready as soon as the handshake completes. For certain types of requests, this can make the connection feel almost instantaneous. The big catch: the replay attack. However, zero RTT comes with a significant security trade-off. It is vulnerable to replay attacks. Imagine an attacker is on the network and captures the client's initial zero RTT flight of data. The attacker doesn't know what's inside, but they can simply copy and replay that entire encrypted blob to the server again. Since the server uses the same PSK from the ticket to decrypt it, it will accept the data as valid a second time. This could be disastrous if the request was something sensitive. The danger of replaying requests. Why is replaying a request so dangerous? Imagine the zero RTT data contain a request like post/API/transfer to equal bob and sign amount equal 100. If an attacker replays this request, they are effectively tricking the server into performing the same action twice, causing the client to transfer money to Bob a second time. This is why zero RTT is not a silver bullet for performance and must be used with extreme care. The server and application need to be specifically designed to handle this risk. The mitigation. Requiring idempotency. The primary mitigation for replay attacks is to ensure that any data sent via zero RTT is idempotent. An idempotent action can be performed multiple times without changing the result beyond its initial application. For example, a GET request to retrieve a web page is idempotent. Fetching it 10 times achieves the same result as fetching it once. However, a POST request to create a resource or perform a transaction is not idempotent. Browsers are designed to only send idempotent requests, like GET, over zero RTT server applications, however, must ensure they do not process non-idempotent actions sent this way. Does resumption break forward secrecy? This is a critical question. If the session keys are derived from a PSK that is stored in a ticket, does that break the forward secrecy we gained from ECDHE? The answer is, not if it is implemented correctly. The security of the PSK depends on the key the server uses to encrypt the session tickets. The TLS 1.3 standard recommends that servers rotate these ticket encryption keys frequently, for example, every few hours. This means that even if a server's ticket key is compromised, it can only be used to decrypt recently issued tickets. Old, recorded traffic remains secure because it was derived from different, older ticket keys. This provides a form of forward secrecy. The best of both worlds. PSK plus ECDHE. To provide the strongest security, TLS 1.3 allows for a combined mode. The client can send a session ticket to resume a session, but also include a fresh ephemeral key share. The server can then use both the PSK from the ticket and the new ECDHE shared secret to derive the final session keys. This provides the best of both worlds. You get the low latency startup of a resumed session, plus the full perfect forward secrecy of a fresh ephemeral key exchange for all the data sent after the handshake. This is the recommended mode for highly secure applications. Summary of handshake types. This table summarizes the 3 handshake modes in TLS 1.3. The full 1 RTT handshake is the default for new visitors, offering the strongest security with mandatory forward secrecy. The resumption handshake offers a faster connection for returning visitors by using a PSK, and still has strong forward secrecy guarantees if ticket keys are rotated. Finally, the zero RTT handshake offers the absolute fastest connection but comes with the risk of replay attacks, so it must only be used for non-sensitive, idempotent data. When to use each type. So when should each handshake be used? The full 1 RTT handshake is the default for any new connection. A resumption handshake is ideal for a user browsing through different pages on the same website. It speeds up navigation without a major security compromise. Zero RTT is a specialized tool. It is great for retrieving static assets like images or CSS, where replaying the request has no negative side effects. It is actively dangerous for any action that changes state, like submitting a form or making a purchase. Conclusion: TLS 1.3 session resumption is a powerful performance optimization that creates a fast lane for returning clients. By unifying the mechanism under a pre-shared key model using session tickets, it enables both faster handshakes and the groundbreaking zero RTT feature. However, this speed comes with a well-understood security trade-off. While standard resumption is very secure, zero RTT must be handled with care to prevent replay attacks. It is a perfect example of the careful balancing act between performance and security that defines modern protocol design. Final thoughts. The introduction of a streamlined and secure session resumption mechanism is one of TLS 1.3's greatest achievements. It directly addresses the needs of a mobile-first internet where latency is a primary concern. By providing different modes, from the ultra-secure 1 RTT to the lightning-fast but specialized 0 RTT, TLS 1.3 gives developers the tools to build applications that are both faster and safer than ever before. Thank you for your attendance. Please consider subscribing to the channel.